A very good day to you wherever you are. My name's Laurence Tratt, and in this video I'll be looking at the challenges of program performance under just-in-time compiling virtual machines, such as the Java Virtual Machine, PyPy, and V8. The scenario I'll be considering is where we have a benchmark running inside a for loop, and we record the performance of the benchmark as the for loop executes. On the x-axis of the graph, we'll record each iteration of the benchmark, what we formally call the in-process iterations. On the y-axis, we'll record the time, the length of each iteration, and we might expect performance over time to look roughly as follows. Execution starts in the profiling interpreter, a general but slow implementation of the language. After a while, we've identified all of the hot parts and have handed them over to the JIT compiler to compile them into machine code. We might expect execution to temporarily slow down at that point, but it's okay, because it gets us to the nirvana, the steady state of peak performance. And nearly all published VM results pertain only to peak performance numbers. But there's something missing from this figure: the time between the program starting to execute and getting to the steady state of peak performance, what's formally called the warm-up time. And this video is all about our attempts to accurately measure this and the surprising results that we found. In order to rigorously evaluate this, we first had to define a scientific hypothesis, which is that small, deterministic programs reach a steady state of peak performance. This intentionally weak hypothesis captures the folk knowledge underlying most VM benchmarking. We then had to decide which benchmarks to use. Perhaps unusually, the benchmarks of the computer language benchmark scheme are absolutely perfect for our situation. They're small and widely studied by VM authors, so we didn't have to worry that we were including weird or unusual benchmarks. We then checked them for what we call control flow graph non-determinism. In essence, we put print statements around if statements, for loops, and so on, and repeatedly ran the programs looking for any change in output. That showed us that the faster benchmark did not reinitialize its random seed on each iteration, which we easily fixed. We also occasionally observed lazy class loading in Java happening in different orders. We fixed that through the careful use of static initializers. We then faced a classic problem with benchmarking JIT compiling VMs, which is that they can be sometimes annoyingly clever, such that they can optimize away a benchmark completely if you're not careful. Sometimes people solve this by putting print statements into the benchmark, but you then end up measuring the I/O performance of your libraries or kernel. Instead, we calculate checksums as the benchmark execute and compare those to an expected value at the end. This makes it difficult, though admittedly not impossible, for the JIT compiling VM to remove the main body of the VM. We then had to think about how long to run the benchmarks for. I knew from my own experience that VMs contain a number of magic numbers, 100, 1000, 1024, and so on, that determine behavior changes, perhaps triggering garbage collection, recompilation, and so on. So we needed to run the benchmarks for more than 1024 in-process iterations. We eventually settled upon 2000 in-process iterations as a reasonable number. We also knew that we wanted to shut down the VMs and run them afresh many times, what we call process executions. We had very little idea what a good value would be for this, but we eventually settled upon 30 process executions. We then ran the benchmarks on a variety of language implementations covering Java, PHP, Ruby, Lua, Python, JavaScript, and, as a baseline and sanity check, C. We also compiled all of the VMs using the same version of GCC so that we don't have to worry that a different C or C++ compiler could color our results. We then ran the experiment on 3 separate machines: Linux 4790 running Debian on a consumer-grade Intel system, Linux E3-1240v5 running the same version of Debian but on a server-class Xeon system, OpenBSD 4790 running almost the same hardware as Linux 4790 but with, as the name probably suggests, a different operating system. We hoped that this would allow us to understand the impact of different hardware and operating systems on program performance. We then did several of the things that I hope all good benchmarking experiments do. For example, we turned off turbo boost and hyperthreading. Turbo boost is a feature that allows your CPU to temporarily execute in a higher performance mode. But we discovered that on some, but not all chips, there are undocumented intermediate turbo boost modes that kick in depending on how many cores are active. We turned the network card off so that, for example, botnet traffic couldn't impact upon performance. and we disabled the standard Unix daemons such as cron and smtpd that can kick in unpredictably and affect negatively program performance. However, we gradually came to realize that there are many other potentially confounding variables which we needed to control. So many that we ended up creating a new benchmarking framework called Cron. Cron does a wide variety of different things, and I don't want to go into all of the details, but I do want to give you a flavor. For example, Cron runs each process execution with the same heap and stack limits so that VMs can't utilize different amounts of memory. It runs each process execution under a clean Unix user account whose home directory is deleted and created afresh after each process execution, so there can't be cache files lurking around between runs. Before each process execution, Cron automatically reboots the machine, so that if one benchmark, for example, pushes the machine into swap, that can't negatively affect subsequent process executions. When it starts, Cron measures all of the temperature sensors in the machine, and it won't run subsequent process executions unless those temperature sensors have returned to pretty much the same value. We did this because we have no real idea if different parts of hardware change their performance characteristics as their temperature changes. After each process execution, Cron checks to see whether the CPU throttled, perhaps because it overheated. If it did, that process execution is rerun. After each process execution, Cron checks the D-message output, and if anything was logged, we're notified. That allows us to see if something odd happened during execution, and indeed that did happen on one benchmarking machine which we threw out from the final experiment. Cron also does various other things, setting tickless mode, CPU governors and so on, but I hope you get the general idea. I also think that's probably enough methodology for now, so let's have a look at some data from version 1.5 of our experiment. What you're looking at here is the Fancouche Redux benchmark running on Luajit on the OpenBSD 4790 machine and the 14th of 30 process executions. On the x-axis we have the 2000 in-process iterations, and on the y-axis the time in seconds of each of those iterations. Notice that the y-axis does not necessarily begin at 0. Sometimes we'll show small insets which zoom in on parts of the data of interest. And in this case, we can see that the benchmark started fairly slow in the top left before quickly becoming a little faster. A while later, it became faster again, hitting the steady state of peak performance. This, I would suggest, is a good example of classical warm-up, albeit it perhaps has taken a little longer than one might have expected, only hitting the steady state of peak performance around 90 to 100 in-process iterations. However, we have 3,660 of these plots in our experiment, far too many to do any sort of manual analysis on. We therefore turn to change point analysis, which is a technique for analyzing time series data such as you see here. We visualize the results of change point analysis as follows. The vertical red lines are change points, and they capture the intuitive notion that the performance data to the left of the change point is different than the performance data to the right of the change point. Between two change points, and there are implicit change points at the beginning and end of the x-axis, we have change point segments. Change point analysis is fundamental to our experiment, allowing us to produce detailed statistics. However, not all process executions warm up in the classical manner. This is nbody running on PyPy on the Linux 4790 machine. The red dot you can see on the noticeably slower in-process execution is an outlier, and as is common with time series data analysis, it's been ignored. In our case, the assumption is that it is perhaps the garbage collector running or the operating system kernel doing something that's caused execution to temporarily slow down, and we don't want that to affect the rest of our analysis. When we look at the process execution overall, we can see that there is no observable warm-up happening at all. It is possible, I admit, that the VM's simply not able to optimize the program at all, but it's rather more likely that warm-up is occurring so quickly that we can't measure it. We therefore realized that we needed to be able to classify the different performance behaviors of different process executions. We therefore designed a simple classification algorithm based on change point segments. If all change point segments in a process execution are equivalent to each other, we classify the process execution as flat. If the final change point segment is in the fastest set of change point segments for that process execution, we classify the process execution as warm-up. That allows us to look at process executions such as faster on V8, which noticeably bounces around at the beginning before settling eventually onto a steady state of peak performance as warm-up. Similarly, spectral norm on PyPy, which has several change point segments but does eventually hit a steady state of peak performance, can also be classified as warm-up. But then we encounter process executions such as this, which is Richards running on hotspot, and the inset may help you see that it starts execution off fairly slowly in the top left before speeding up noticeably. But then at the 200th in-process iteration, it slows down. It's hit a steady state, but it is not peak performance. This gets even more interesting when you realize that Richards is one of the benchmarks used to verify hotspot's performance from the very beginning of its existence. We thus need to update our classification algorithm, saying that if the final change point segment in a process execution is not in the fastest set, we classify it as a slowdown. That lets us observe, for example, faster on V8 bouncing around a bit and again hitting a steady state, but not of peak performance. And then we see our final type of process execution. Here it's binary trees on V8, which bounces around endlessly without hitting a steady state of peak or non-peak performance. Perhaps if we'd run the benchmark for longer, it would have settled down, but we have to have a cutoff somewhere. And thus we can get to the final step in our classification algorithm. If none of the other clauses are matched, we have what we call a no steady state process execution. We consider flat and warm-up to be morally equivalent because, after all, a flat process execution may simply be one in which we couldn't measure the warm-up happening. But in their different ways, we consider both slowdown and no steady state to be bad since they both subvert traditional expectations of program performance. The classification algorithm is far more consistent than a human could ever hope to be, but there are always going to be some edge cases. Consider Pfannkuche running under hotspot. If you look at the steady state of peak performance here, you may notice that it's actually a square wave predictably going above and below the change point segment. It's shallow enough that this process execution has been classified as warm-up, but depending on the version of hotspot, that square wave becomes deeper and it can be classified as no steady state. Personally, I'm comfortable with that either way. There are always going to be a few edge cases like this, but the classification algorithm is remarkably effective overall. It allowed us to uncover interesting results such as this, which is binary trees on V8 on the same Linux machine. The left-hand side process execution warms up, the right-hand side process execution is in no steady state, thus showing that VMs do not always behave predictably even in the same environment. On this example, you can see binary trees on C on the left-hand side on a Linux machine and on the right-hand side on the OpenBSD machine. On the Linux machine, this benchmark undergoes a clear bouncing ball pattern and is thus a no steady state. The OpenBSD machine is classified as a flat process execution, but notice how much slower the OpenBSD process execution is. This is probably due to different malloc implementations, OpenBSD's preferring security over performance. Ultimately, we take all of this data and produce these wonderful looking tables, which are also completely unreadable at this resolution. So I'm going to zoom in on the spectral norm data in the bottom right. Let's try and make sense of some of this data, and we'll start with the V8 row. This squiggle shows that all 30 process executions warmed up. The steady state was reached in the median case at 3 in-process iterations at a time of just over half a second. The mean performance of an in-process iteration in the steady state is 1/4 of a second. The histograms show the distribution of data, with the blue bucket showing as appropriate the mean or median value. If we look, for example, at Graal, we can see that all 30 process executions slowed down. Now, it's not always the case that all process executions do the same thing. If we look at PyPy, 27 process executions were classified as flat and 3 as warm-up. We therefore classified the overall result as what we call good inconsistent. In contrast, HHVM had 29 process executions which warmed up, 1 no steady state, and thus the result is what we call bad inconsistent. The final thing we need to look at here is Luajit, which shows a single dash symbol. All 30 process executions were flat. It therefore doesn't make sense to worry about the steady state iteration or time. Aggregating data allows us to understand something about the bigger picture. The OpenBSD data needs to be treated slightly differently, so let's ignore that. And let's start with the Linux 4790, a column at the bottom part of the figure. The way to read this is as follows. 22% of all process executions were flat, 48% were warm-up, 20% were slowdown, and 9.6% in no steady state. If we look at the top part, we can see something slightly different, and this tells us about VM benchmark pairs. 8.9% of benchmarks were flat across all 30 of their process executions. 20% were warm-up across all 30 process executions. And 11.1% contained a mix of flat and warm-up. In other words, we consider those good, inconsistent, and equally good. That means that roughly 40% of benchmarks were consistently performing as per traditional expectations. But at about 9% either consistently slowed down or were no steady state. And at over half are bad inconsistent, sometimes either slowing down or having a no steady state. If we take an even higher level view, things look even more worrying. About 67 to 70% of process executions warm up as per traditional expectations. But only 37 to 40% of VM benchmark pairs consistently warm up as per traditional expectations. And when we factor in the different machines, only 12.5% of benchmarks consistently warm up as per traditional expectations across all machines. This, to be blunt, is not what we expected to see. Are there any simple explanations? To try and find out, we did a separate run of the experiment for those VMs that enable performance counters. Here you can see faster running on PyPy, and at the bottom you get the main plot clearly showing a no steady state. In the top you can see how much time was spent in garbage collection and JIT compilation for each in-process iteration. The time spent in garbage collection clearly correlates with the wall clock time of each iteration in the bottom. This was a memory leak which we reported to the PyPy developers. Here's our old friend the Richards benchmark running on Hotspot, which slows down at the 200th in-process iteration. Just before that happens, there's a significant just-in-time compiling event. So probably the Hotspot is trying to recompile the program and accidentally slowing it down. Knowing that is surprisingly unhelpful. The JIT compiler is a massive component, and that doesn't really narrow down the search for what the real cause might be. This is Fankush on Hotspot, the square wave example we saw earlier. Turning on the performance counter slightly fiddles with the square waves, but they do reappear around about the 1000th in-process iteration. However, there is nothing I can see that correlates in garbage collection or JIT compilation that explains the square wave. Honestly, most examples looked more like this than the preceding two. We were very rarely able to see any plausible explanation which explained the poor behavior we saw. So how, as a field, have we got ourselves into such a pickle? Well, if I knew the real answer to that, I'd be very rich, but what I can do is offer you a couple of thoughts. The first one is that benchmarks can sometimes lead us astray. Several years ago, I was talking to someone at Dropbox who were using Python, and they had various performance problems that they tried to solve by using PyPy, but it hadn't helped. They'd condensed the problem down to a single simple benchmark which they sent me, and when I looked at it running under PyPy, I realized that PyPy was unrolling recursive function calls. If you know anything about compilers, you'll know that unrolling is a very powerful but exceedingly dangerous optimization that you only enable in rare situations. I therefore thought it would be interesting to have a look at the problem. A couple of days later, I developed this simple fix that you see on screen. It made the Dropbox benchmark over 13 times faster, which is good, but it also made some existing PyPy benchmarks run slower, which is bad. I knew, quite reasonably enough, that the PyPy developers probably wouldn't accept my patch if it made those existing benchmarks slower. Via some not very good quality experiments, I determined that if I allowed 7 levels of recursion but no more to be unrolled, the existing PyPy benchmarks were not negatively impacted, and the Dropbox benchmarks ran almost as fast as it did before. I thus proposed to the PyPy developers my fix, allowing 7 levels of recursion to be unrolled. It was accepted, and I think it's still in there today. And I proposed that 7 levels of recursion were unrolled, even though I'm convinced that's the wrong value. I'm almost certain that no recursion at all should have been unrolled. But that's just my gut instinct. The benchmark suite did not back me up, and I had to defer to the benchmark suite even though I worried, and still do, that it had led us astray. However, there is a worse problem. A little while later, I was investigating the Octane benchmark suite for JavaScript, which at the time was one of the most popular JavaScript benchmark suites. I downloaded it and quickly altered the harness to run each benchmark for, you guessed it, 2000 iterations. When I ran it, I saw the following error, which even a JavaScript neophyte like me can realize is probably the result of too much memory being used. I thus did some very simple benchmarking to see how long each iteration of the benchmark was taking, and there's an interesting looking hump around 70 in-process iterations, but it's difficult to see exactly what's going on. So I recorded the data at a slightly finer grained level, which definitely looked more interesting, but which was obscured by the last few in-process iterations. When I chopped those off, I got the following. And if I've ever seen data which suggested a memory leak and a garbage collector thrashing, this is it. However, I knew virtually nothing about JavaScript, and I thought my chances of finding a memory leak in what is a very large benchmark were nearly zero, but I thought I'd have a look anyway. I loaded the benchmark into my trusty text editor and almost immediately noticed a global variable called canvas logs with what looks like an empty list. I searched for every reference to that variable and there's only one, where data is pushed into that list. To my astonishment, I'd found the problem in 30 seconds. Then took me about 10 minutes to work out how to clear a list in JavaScript, but with a one-line fix, the memory leak was solved. It might not be obvious why this is a problem, but let me give you two reasons. First, the longer you run the benchmark, the more you're measuring just the performance of the garbage collector, especially in tortuously low memory situations, than you are any other aspect of the VM. Second, Octane, like many benchmark suites, has a mode where you can run as many iterations of the benchmark as possible in a given time period. Because each iteration takes slightly longer to run than the one preceding it, this can give you a false idea of the effect of any optimizations in your VM. Although I didn't investigate too much further, PDFJS is clearly not the only problematic benchmark in the Octane benchmark suite. The code load closure benchmark also has a clear memory leak. Zlib has something which might be a memory leak, and overall timings are made with a non-monotonic microsecond timer, giving you inaccurate and misleading timings. So what can we do to fix such problems? Well, I have some simple suggestions which might help alleviate the problem slightly. First, simply running benchmarks for longer uncovers all sorts of performance issues which VM developers can then use to fix their VMs, and that's one of the simplest and most powerful things I learned from our experiment. Secondly, neither peak performance nor a steady state may necessarily occur, and benchmarking methodologies which presume those are broken. I think we should always report warm-up time. Users always experience it, they care a great deal about it, and we should focus on it more. I think we overtrain on small benchmarking suites, and we could learn from the machine learning community who separate out the idea of training and validation suites. We need more benchmarks. Most benchmark suites are far too small. We need many, many more benchmarks. And finally, I think we need to focus more on predictable performance rather than trying to make some small programs run insanely fast. Most users would be happier if we made more programs run predictably fast. Before I finish, I'd like to thank EPSSC in the UK for funding the Cooler and Lecture Fellowships, and also Oracle and Cloudflare for their funding. This research wouldn't have been possible without all of their help. All of the good bits of this video have been based on the hard work of Ed Barrett, Carl Friedrich Boltz, Rebecca Killock, and Sarah Mount. And if you want to read their wisdom and hear rather less of my ramblings, I'd encourage you to read the original paper at soft-dev.org. If you want a slightly easier introduction to the topic, you might find this blog post of mine a useful complement. Thank you very much for listening.
Wow. Thank you so much, Louis. That was a really great talk. And it's surprising to see that in the end, the benchmarks that, like you said, people overtrain towards might actually be leading them down the wrong valley. I really like that analogy. So what do you think? Who should take action on this? Should the benchmark makers make their benchmarks better, or?
Probably the answer is everybody. We need more benchmarks, and I was going to say better benchmarks, but that's unfair because every benchmark is imperfect by definition. So if we have more benchmarks, and assuming those benchmarks aren't just clones of each other. So for example, if I had 100 benchmarks that are just the Fibonacci benchmark in disguise, that wouldn't be very helpful. But assuming there's some diversity of our benchmarks, more is better. I think as VM developers, I think we need to benchmark our VMs more carefully. And I think we need to focus on the issues that users actually care about. Peak performance is the metric that makes us look the best, but it's not the only metric the users experience. So by focusing just on peak performance, we're not giving users the best overall experience.
Okay, so in the end, the power should lie with the VM developers because they are the ones that actually want to improve the product. Sorry, power is maybe the wrong word, but they are the
responsibility. Yes.
Responsibility. Okay, and I was really impressed when you said you had to go against your gut instinct on the PyPy example just because the benchmark told you so. So do you still regret that, or do you still think it was the right thing to do?
Though it was still the wrong thing to do, but it was the only thing. It was better than doing nothing. And what I think is the correct fix, which is no unrolling of recursion. If I'd tried to fight on that hill, I would have lost. So there's always an element of pragmatism, and also I think another aspect that is sometimes forgotten about with benchmarking, particularly VMs, is it's not always realistic to expect that we make everything better. Sometimes we put in an improvement, and if we've got, say, 100 benchmarks, 98 of them will get faster and 2 of them will get slower. So you're always, in my opinion, in a mature system, having to balance out the fact that there aren't many changes which are a complete win. There's always a little bit of to and fro. So, taking that into account, I think the change was better than nothing, but I still wish the value was 0.
And I really like the very last point you made around predictable performance and how that's actually probably more important to the end users than the peak performance. Do you see people agreeing to you? Are the VM developers saying, "Yeah, we should start marketing that versus peak performance"? Or
that's an interesting question. So, I mean, a lot of the VM developer community have heard me talk at them on this stuff over a few years. I mean, the data is actually a few years old, but I went and tested one of the VMs last week just to check, and it has exactly the same performance problem as when we benchmarked it in 2017 or 28. I think the data is actually from 2018, maybe. So I think a lot of developers probably would like things to be better, but it's also very difficult. We had a project looking at trying to fix Luajit just a year long, and we tried using some of the benchmarking techniques we came up with, and we spotted some real problems, and we managed to fix some of the very small and simple ones, but we tried tackling one of the big performance oddities we saw, where after a few minutes, a benchmark which represented a real program just went bonkers slow, and all sorts of odd things happened. And we were not able to fix that except by completely rewriting the garbage collector. And, that's an incredibly big fix. We actually weren't able to finish that within the duration of the project, unfortunately. But that gives you a suggestion that we couldn't narrow it down. Clearly, there was some interaction, and it may not even have been the garbage collector itself that was causing the problem, but it may have caused an interaction with something else. We couldn't work that out, although we could tell that replacing the garbage collector with a better one would fix the problem. And Luajit is, as these things go, a very small VM. You scale that up to a hotspot or a V8. These are massive systems, hundreds of thousands of lines of code, and it's possible that a performance problem is just one line somewhere that's just slightly wrong. How difficult is it to find that? Insanely difficult. So I think people would like to make things better. I think broadly they would agree that we're not quite where we would like to be, but that fixing it is insanely difficult. But there is an optimistic note as well, which is I think that our VMs could run quite a lot faster than they currently do. In other words, we don't really know what the best performance you can get out of a VM is, but I think we can probably get quite a lot more than we've managed so far if we can start to narrow down and fix these performance issues over time.
And I mean, hearing you talk about it, I wonder if you probably reach out to the actual end users of the VM themselves, because if I don't know if the AWSs of the world hear that there is some optimizations to be done, given the culture of Amazon, probably they will be very persuasive.
Yeah, but it's fixing it would be difficult and expensive, and it's not. Some of the performance problems may be so deeply embedded that they're not fixable in a practical sense.
Okay.
So, for example, in hotspots, and I know that there will be other VMs because I've developed another VM that deliberately does the same thing. There's a counter on a function that says how often has this function been called, and should I compile it? That counter is updated in a sense non-atomically because it's a bit expensive to do it atomically. So it means that it's non-deterministic in the multi-threaded program when that function will be compiled. If you've got multiple threads, different threads may notice that the counter has hit the threshold at different points. Those different threads may have different profiling data even for that method and compile it differently. You can have multiple threads compiling it and it's non-deterministic which wins. There's this pile of non-determinism. And that's just a simple example, but that's that aspect is semi-fundamental to how things work. If you wanted to change that, you'd have to rewrite very large chunks of the VM. So it's difficult to take out those things that you just kind of have to live with what I would call perhaps more clear performance bugs, where the garbage collector just doesn't do the right thing. It goes into low memory mode too soon or something like that.
Got it. But Laurie, thank you so much for your time and for your talk today.
My pleasure.
Hopefully we'll get to see you a bit at panel time. Have a great day.